Hey everyone, welcome. This is assignment 50. Woohoo! Um, Polynomial applications, i.e., word problems. So I want to say something about um, word problems. Remember, we had that nifty little shortcut formula for linear word problems. Ending amount equals rate of change times the input variable plus the starting amount. And that works really well. And we don't have something like that for these problems. Some of them, some of these problems, you will have no difficulty doing um, because you'll say, I know all that. For example, the box problems. The box problems are going to be here. You've already seen them once. You're seeing them again now. I imagine you'll see that box 3 times, maybe 4 this year. Um, there are other types of problems, though, that are definitely thinky problems, and I want to start off with one of those now. This is a very good problem for people going on to calculus. So we're told that there exists this function, f of x, and on these intervals, we get function values. So from negative infinity to negative 4, this function, f of x, is above the x-axis, has positive y values. But between negative 4 and 0, this function now has negative values, okay? Negative y values. From 0 to 1, they're negative again. Well, isn't that interesting? Why didn't they just go negative 4 to 1? I wonder what's happening there at 0, that the function values are negative here, the function values are negative here. What must the value be at x equals 0? Well, since 0 isn't included and these are negative, I think 0 has got a value of 0. I think 0 is an x-intercept for us. But we'll come to that in a little bit. So these are domain intervals, and these are function values. What is f of x doing? Where is f of x on each of these intervals? And now we have some questions. There are 5 really cool questions here. So first question is, where are the zeros? And you can think of those as x-intercepts. Well, as my function goes from positive to negative, I must pass through a value of 0. So I think as my function is still positive at negative 4, or going up to negative 4, but after we get to negative 4, the function is negative, I think x equals negative 4 is one of my x-intercepts. I then see that my function goes from negative to negative at 0, but they didn't write negative 4 to 1 negative, and so that I would know at x equals 0 the function was negative. Instead, they said negative 4 to 0 and 0 to 1 negative. So here's 0, and I'm negative on this side, and I'm negative on that side. But I think since 0 isn't included, I must be 0 at x equals 0. And then finally, when my function goes from negative to positive, that happens at x equal to 1. And so I think x equals 1 is a 0 as well. So there's the first question. Where are the zeros of this function? At negative 4, at 0, and at 1. Okay, that's part A. Part B, what's happening at x equal to 0? Yeah, well, so okay, there's this x-intercept here. And to the left of x equals 0, or between x equals negative 4 and x equals 0, this function is negative. And maybe it curves like this, and maybe it curves, I don't know, just draw something. Okay, but after 0, until I get to 1, this function is negative again. So what do we have happening at x equals 0? Yes, it's an x-intercept, but look, we have a bounce. So what does that tell me about the x minus 0 factor? Is it to the first? No, we would be going through. Is it to the third? No, we're not wiggling through there. It's to the second. and we have a bounce that tells us that. Okay, so we have a bounce at x equals 0 is the answer to part B. C, what's the least possible degree and why? Okay, so we said that we would have x-intercepts at 4, at 0, and at 1. Is this a third degree polynomial? No, it has to be higher than that. Why? Because of the bounce here at 0. So I could imagine x plus 4, x minus 1, but here, x minus 0 squared. And yes, I would write that this way. And so I think the least possible degree is squared times x is x to the 4th. I think the least possible degree here is 4th degree. Okay, next. Can this be an odd degree polynomial? Well, based on what I see here, where my function has to be positive up here but negative here, and then bounce at 0 we already talked about, and then from 0 to 1 my function is negative, but after 1 my function is positive. Look, both ends go in the same direction. If both ends go in the same direction, then I can't have an odd degree polynomial. This has to be an even degree polynomial. Okay? Okay, so that's part C. Part D, the leading coefficient. Is the leading coefficient here positive or negative? What can you tell me about the leading coefficient of this polynomial? Positive or negative? I agree. I agree that this has to be a positive leading coefficient because both ends are going up, not both ends are going down. If both were going down, I'd say there's a negative leading coefficient. Both are going up, so I say positive leading coefficient. Okay, and then part E says write an equation for f of x. Okay, well, so here's f of x. X minus 0 squared, x plus 4, x minus 1, based on just this information. Now, you might choose to put an a value here, and any positive number will work. So 17 is a possible function. 1/2 is a possible function. But for most of us, we're just going to leave it like this. If I did have a negative leading coefficient, I would have to put a negative there, though. Okay? All right, well, now, that was me doing one. How about you doing one now? Okay? So let's look at this situation. Still the same sort of intervals and function values. Here, this time we have negative infinity to negative 4, and we have negative 4 to 0, and we have 0 to 1, and we have 1 to infinity. However, now we have positive, negative, positive, negative. How does that change things? Kind of looks the same. I'm looking for the same information. I'm looking for x-intercepts. I'm looking for degree. I'm looking for leading coefficient. Is it positive or negative? So what can you tell me? And then I'd like you to write a possible f of x here. I'd like you to write a possible function. Okay. So what do you think? Function goes from positive to negative. Function goes from negative to positive. Function goes from positive to negative. You should pause the video and give a chance to try and think about this. Come back when you're done. So here's my negative 4, my 0, my 1. I know from negative infinity to negative 4, the function is up here. I know from negative 4 to 0, the function is down here. I know from 0 to 1, the function is up here. Ooh, so there must be some sort of bendy thing happening there. And I know from 1 to infinity, my function is down here. So I guess, again, there's going to have to be some bendy thing there. So what do you think? What can you say about this? Well, I myself have a hard time thinking about it just from the table. But with this picture, I think, oh, look, there are x-intercepts at these places because my function goes from positive to negative or negative to positive, and therefore has to pass through a function value of 0 on the way. Well, that's good. Next question was, what about degree? Well, I got 3 x-intercepts, so the least possible degree is x to the third. It could be x to the fifth, it could be x to the seventh, but I do think it has to be an odd degree polynomial. Why do I say that? Well, so yeah, I could be passing straight through all these, but what if I was actually wiggling through all of these? And so that's got to be third, sixth, ninth degree. So I could have higher degrees, but I think the least possible degree is 1 x-intercept, 2 x-intercepts, 3 x-intercepts, so third degree. Okay, and the leading coefficient, is this a positive leading coefficient or a negative leading coefficient? Does this look like a positive x to the third or negative x to the third? I agree, negative x to the third. This has the end behavior of negative x to the third, not x to the third. So, can we build a function? Sure. We can say x plus 4, x minus 0, x minus 1. There's our third degree polynomial. Oh, with a negative leading coefficient. Good. And of course, you could put any negative number you want here. I'm just going to go with the negative sign. All right. So I think you might be getting a little less frightened about this. Let's try one last one. So we have our intervals and our values. We've got negative infinity to negative 2. We have negative 2 to negative 1. We have negative 1 to 3. We have 3 to 4. We have 4 to infinity. This is negative, positive, positive, negative, negative. All right, so find the x-intercepts. Tell me about the least possible degree. Tell me what's happening at x equals negative 1 and what's happening at x equals 4. And tell me about the leading coefficient. Is it positive or negative? So that's a lot of stuff to think about. In fact, why don't you write me a possible f of x function while you're at it? Okay, so I want x-intercepts, I want leading coefficient, I want least possible degree, I want a function, and I also want you explaining what's happening at negative 1 and what's happening at positive 4. Okay, so pause the video, come back in a few minutes. I'll see you then. Hey, welcome back. So we've got negative 2 here, negative 1, 3, and 4. And I know the function is negative over here, and the function is positive over here, and then the function is positive again. Function is positive again. But at negative 1, see, we're split here. At negative 1, we are not positive. Well, we're 0. So I have to bounce off of there. Okay? So I've got to bounce at negative 1 as the function goes from positive to positive, but is not positive at negative 1. The function has a value of 0 at negative 1, which means the function has an x-intercept at negative 1. All right, what about as we go from positive to negative? At 3, we go from positive values to negative values. Okay? And then at 4, my function values go from negative to negative again. And I think that's the same thing that we saw here at negative 1. Bounce as I go from negative to negative. Notice how 4 is not included. So at x equals 4, the function value is not negative. That tells me the function value needs to be 0. So I see here 1, 2, 3, 4 x-intercepts, but I see a bounce here and a bounce here. I also notice that both ends are going down. So I think I have an even degree polynomial with a negative leading coefficient. I think I can write the factored form of that polynomial, where x plus 2, and x plus 1 because of the bounce squared, and x minus 3, and x minus 4 because of the bounce squared. And so here's a 6th degree polynomial, 2, 3, 4, 5, 6. Did we answer all the questions? We found the x-intercepts. We explained what was going on at 4 and negative 1. We talked about the leading coefficient. And the least possible degree is 6. It could be higher. It could be 100. But what we know is minimally we have to have 6 because this is 2 and this is 2 and each of these are at least 1. Now, I don't know that I'm not wiggling through here and I'm not wiggling through here. And if I wiggled here, this would be 3, 4, 5, 8, 9, 10. 10th degree. 10th degree is possible. But I think the least possible degree is 6. Okay. So, expect to be able to do something like that. Now, let's go back and just to humor me a moment, y equals 2x to the 4th minus x to the 3rd plus 49x squared minus 25x minus 25. So we've got this 4th degree polynomial, and I'm going to tell you that 5i is one of the zeros. So, will you write this in factored form for me, please? It's going to take a few minutes. You might want to pause the video, go back, work, and then come back when you're done. Okay, welcome back. So I'm thinking about this problem as an opportunity to do some synthetic division. I will say that whenever I have these imaginary roots or irrational roots, leaving as much space as possible cuts down dramatically on the mistakes. I see students who want to write it like this because that's them. They write things small. But when you have to do this problem with this little space, you are going to make so many mistakes. So really, spread it out. You can still write small, just spread it out. You'll be so much happier you do. 2 times 5i is 10i. This has an I, this does not, so I have to write like this. Now I have to multiply that 5i times each of those. Negative 1 times 5i is minus 5i. 5i times 10i. Let's think about that. 5 times 10 is 50. I times I is I squared. I squared is negative 1. So we have minus 50. Now we can combine these and get negative 1 minus 5i. And now have to multiply that 5i times negative 1 minus 5i. And so I'm going to have negative 5i. 5 times negative 5 is negative 25. I times I is I squared. But since I squared is negative 1, negative times negative is positive. So I'm going to have positive 25 minus 5i. Hey, look, I can add these together. And so I just get negative 5i. And then I'm going to multiply this 5i times this negative 5i. 5i times negative 5i. And I'm going to get negative 25 I squared. I squared is negative 1. Negative 1 times negative 25 is 25. And sure enough, 5i is a 0. And I know 5i is a 0 because I'm using the factor theorem. The factor theorem says when I get a remainder of 0, I found one of the roots of that polynomial. And I remember that imaginary roots always travel in conjugate pairs for safety. Okay, so 2 times negative 5i is negative 10i. And I add, conveniently that goes away, and I just have minus 1. Negative 1 times negative 5i is plus 5i. Oh, look, how convenient. These cancel, and I'm left with negative 1. And when I multiply negative 5i times negative 1, I get positive 5i. And when I add these, I get 0. So this is also a root of that polynomial. But look where we are now. We were at 4th degree. we went to third degree, and now this is second degree. This is 2x squared minus 1x minus 1, and we should be able to factor that. Is this the complete factored form? Well, no. When we FOIL this, we only get a second degree polynomial. On your test, it says completely factored, right? And so we need 4 factors, 4 linear factors. Oh, there they are. X minus 5i and x plus 5i. 4 linear factors for our 4th degree polynomial. Okay? All right. And we've got a little more practice with that. Y equals 4x to the third plus 23x squared plus 34x minus 10. And this time I'm going to tell you that minus 3 plus I is one of the roots. All right, so get me some factored form. I want this polynomial completely factored. Okay, come back when you're done. Poor stuff. Well, so welcome back. This is what we said. We could do this one of 2 ways. We could either do synthetic division, in which case it looks like this. This times that, this times that. Can't add this to this, but I can add that to that. And so I get 11 plus 4i. Now I have to multiply this times this, which is going to involve some FOILing. Negative 33 plus 12i, no, minus 12i, plus 11i plus 4i squared, which is minus 4. So I'm going to have negative 37 minus I. Okay, and let's add these. Negative 37 plus 34 is negative 3 minus I. And now I'm going to multiply negative 3 plus I times negative 3 minus I. And so I get 9 plus 3i minus 3i minus I squared. Well, I squared is negative 1. So minus I squared is going to be minus a minus 1 or plus 1. So 1 plus 9 is 10, and these middle terms cancel, 10, and therefore 0. Well, that's great. I wanted a 0 there. And I know if I'm given a root and I don't get 0 over there, there's some kind of mistake going on here. Remember, complex roots always travel in conjugate pairs, so 3 minus I is also a root. 4, negative 12 minus 4i. Oh, look, those cancel. And here, I just get negative 1. And then I'm going to multiply this times the negative 1, and I'm going to get 3 plus I. Whoa, they all cancel. So I get 0. So this must be my last factor. 4x minus 1. Third degree, second degree, first degree. Don't forget, though, if you're supposed to write this in completely factored form, I still need x minus 3 plus I and x minus 3 minus I. Okay? So, and of course, you could distribute those negatives if you wanted to. So this was one approach to the problem, where I just did that synthetic division. But remember, we have this other way of doing this problem. If negative 3 plus I is one of the roots, then we know negative 3 minus I is another one of the roots. And I can turn these roots into factors. And so now I am going to do this distributing, and I'm going to have x plus 3 minus I times x plus 3 plus I. And guess what I need to do? I need to FOIL here, okay? And I think the feeling bad about and not wanting to do and the complaining about FOILing always takes much longer than actually just doing the damn FOILing. So do the damn FOILing. This times each of these, and that's what colored markers were made for. So this goes to each of those, and I'm going to have x squared plus 3x plus xi. And then I'm going to multiply this times each of these. And I'm going to have 3 times x, and I'm going to have 3 times 3, and I'm going to have 3i. And then I'm going to do negative I times each of these. So I have negative xi minus 3i, and then negative I times positive I is negative I squared. Okay. And remember, 3 things times 3 things, there better be 9 of these things. 3 times 3 is 9. That's always good to sort of check to make sure you didn't miss anything. Well, what do you notice? Oh yes, these are opposites, so they cancel out. And here's a plus 3i and a minus 3i. They cancel out. And here's a plus 3x and a plus 3x. So I think we can write that as plus 6x. And now what about this? This is minus I squared. Well, I squared is negative 1 with a negative in front of it. So that's plus 1. 9 plus 1, 10. Okay? So we can turn these roots into factors. We can FOIL those factors to get this polynomial. And now we can do some long division. X squared plus 6x plus 10 into 4x to the third plus 23x squared plus 34x minus 10. So what do I have to multiply this by to turn it into that? A 4x. And so 4x times this, and 4x times that, and 4x times that. And remember, because we're doing long division, we're subtracting. So I have negative x squared minus 6x, and I bring down that minus 10. Okay? And look. What do I have to multiply this by to turn it into this? A minus 1. And when I distribute that minus 1 to each of these, and when I subtract, I get 0. So there's my third factor. So, again, x minus 3 plus I, x minus 3 minus I, times 4x minus 1. So, 2 ways to do it. FOIL these out and then do long division, or take that and use synthetic division, then take its conjugate friend and do synthetic division, and this will be what you're left over with. You gotta get comfortable with one of those 2 approaches before we have our test, please. Okay, next, speaking of common word problems, and the post office, which still exists as of the making of this video, the post office says that the girth plus length can't be bigger than 120. And I'm going to imagine we're going to send the biggest box we can. So we're not going to do an inequality here. We're just going to do an equal here. Okay. This is a square-based box, and it has a length. Now, girth is the perimeter of the cross-section. So this is the girth. The girth in this problem is 4x. X plus x plus x plus x. The perimeter of that cross-section is the girth. Plus the length is 120. Okay? Now, let's talk about what this problem wants. This problem is going to say, 1, find v of x. 2, graph v of x. And 3, find the dimensions that make maximum volume. So we can send the biggest package, okay? So now I remember from middle school, Mrs. Rowan taught me in the 7th grade that the volume of a box like this is length times width times height, length times width times height, or length times width times height. I don't care, you just got to multiply them all together. So v is x times y, or v is x squared y. Now, we're not done yet, because this says volume as a function of x. So my equation for volume over here can only have x's in it. Somehow I have to get rid of that y and replace it with some x stuff. Oh, I wish I had a helping equation that I could solve for y and then plug in there to get rid of my y. There's my helping equation. I'm going to solve this equation for y equals by subtracting 4x from both sides. Y equals 120 minus 4x. Now, when I see y over here, I can replace y with this x stuff. So what am I going to get? Well, v of x will be x squared times 120 minus 4x. Oh, look, it's all in terms of x's now. That's great. So next we're supposed to graph v of x. All right, how do I graph v of x? Well, look, I have x minus 0 squared, so I know there's an x-intercept at 0, and it's a bounce. And over here, when I set this equal to 0, 120 minus 4x equals 0, 120 equals 4x, x equals 30. There's another x-intercept. So, too small, no space. Let's go and fix that. So we said there was going to be a bounce at 0, and we're going to pass through 30. We had volume as a function of x equals x squared times 120 minus 4x. Now tell me, if you distribute, do you have a positive leading coefficient or a negative leading coefficient? Well, I see negative 4x to the third plus 120x squared. I have a negative leading coefficient, so I have to start up here and end up going down there, because I have a negative x to the third. We said because of this 2 that we were going to bounce at 0, and then because this is a multiplicity of 1, I'm just going to pass through at 30. Okay? So here's my volume equation graphed. And remember, these are volumes, and these are x's over here. Okay, so let's talk about the domain of this volume function. Well, the domain of any polynomial is, of course, negative infinity to positive infinity. But in this situation, we are talking about the real world. And in the real world, you can't have a box with a negative volume. Not yet, you can't. Maybe some of you will figure out how to do that. That'd be so cool. Okay, but right now, no boxes with negative volume. Now, these are x's, right? X's. Can you have a box with a negative side length? No, no negative side lengths to our box. I dare you, make a box with a side length of negative 5 inches. And so it looks to me like our domain is going to be 0 to 30. Okay? So somewhere on this domain from 0 to 30, we have a maximum volume. And many students like to say, halfway in between those, they're going to have their maximum. Yeah, it almost never works out that way in polynomial land. So because we haven't learned calculus yet, there's a really easy way to do this with calculus. Without calculus, we must take out our calculator and do second calculate maximum and go through that process again. I sure hope you haven't forgotten it since our graphing calculator lab. And if you have, well, maybe it's time to go back and watch that calculator lab video again from our graphing basics unit. I want to say that it was something like 7 in class. 7 in class is the calculator lab. So go watch that video again if you don't know how to find that max there. Okay? So I found that when x equals 20, I get a maximum volume. What is that maximum volume at 20? Well, if I take that 20 and plug it in there, I could find out my maximum volume. I could even do negative 4, 0 placeholder, 120, 0 placeholder, negative 4, negative 80, negative 80, 1600? I think so. 0, 0, 16. Well, that wants to be negative, though. I'm supposed to add those, so I'm going to have negative 1480. No. Well, that's going to give me a negative number. I don't like that at all. Ew. So instead, because I don't want to waste your time while Poopla figures it out, I'm going to go back to x squared and 120 minus x, and I'm going to evaluate this at 20. So that's going to be 20 squared times 120 minus 20, which is 400 times 100, and I get 40,000. Okay, so that's a nice big volume. But what are the dimensions of that box with the biggest volume? Well, right now we only know the x value. 40,000 isn't the y value. This is volume, not y. Remember we had that helping equation? That helping equation was 120 minus 4x equals y. We know the x value is 20. 120 minus 4 times 20 equals y. 120 minus 80 equals y, and so y must be 40. So the dimensions of the box, x is 20, y is 40, so I have 20 by 20 by 40. These are the dimensions of the largest box that I can send through the post office. Nice. All right. Any questions about doing this? Fabulous. Let's move on then. And yes, one of these box problems, or remember this other box problem where you're given this flat sheet and you're going to cut squares out of each corner and fold up along the dotted lines to make this open-topped box. Yeah, I would expect at least one of each of those volume of box problems to show up on our next assessment. Okay, so now let's see, we took care of that, we took care of that, we took care of that. Oh, we're almost done. We've only got practice to do. All right, so let's do some practice, and I think this will be good for you. Y equals x to the third minus 3x squared plus 4x minus 12. So will you A, find the complete linear factorization of this function, and that just means write it so that all the factors are linear factors, and B, graph the function. Okay, go to it. You have all the skills. Look, you really do have all the skills. If you can write this in factored form, you know how to draw that graph. So get it in factored form. 4 terms. What do you think you should do? Yes, grouping. Go, now. Welcome back. How did your factoring by grouping go? I took an x squared out and have x minus 3. I took a positive 4 out and have an x minus 3. By the way, some people just say, I'm taking 4 out. And I've seen this happen to students. They do this, and then they write this answer. X squared plus 4. No, that's not what they do. What is it that they do? They do, oh, yeah. X squared, x minus 3 times 4 times x minus 3. And then they say, look, I've got 2 of those. That's x minus 3 squared, and x 4, x squared out in front. And now we've turned our 3rd degree polynomial into a 4th degree polynomial, and we're very sad. So I strongly recommend that you, when you say I'm taking 4 out, you take positive 4 out. So we have x squared plus 4, and we have x minus 3. Okay? Are we done with the complete linear factorization? No, that's not x to the first. This is not a complete linear factorization. I need to break this down further. So let's since many people are not comfortable seeing this as a difference of squares, let's go the other route where we find the x-intercepts, albeit here they're imaginary. And then we take those zeros of the function and we turn them into factors. X minus 2i, x plus 2i, because that's minus a minus 2i, and don't forget dear old x minus 3. So, your graph, it's only got one real x-intercept. It's positive x to the third. I know where the y-intercept is at negative 12, so let's graph what we've got. 3, negative 12, and this is to the first, so I'm just passing through. And so I'm looking something like this. Now look, these, if this were honors pre-cal, I'd want to have a more accurate graph. Why don't you graph this on your graphing calculator and see how close ours is to it? You know, I'm willing to be that flexible. Because in the age of the graphing calculator, you can just graph the thing on the graphing calculator. We need fast graphing. All right, but what about this one? Y equals x to the third plus x plus 10. Okay, again, I want the linear factorization. Again, I would like to see the graph of this, or a graph of this, okay? All right, come back when you're done. Well, you're back awfully early. Yes, I agree. I can't factor that polynomial with money in my factoring techniques. And I agree. No one gave me something to start my synthetic or long division with. What was that third thing we were supposed to be doing? Right. When those two things don't work, I'm supposed to graph this on my graphing calculator and use my eyeballs. I'm supposed to use my eyeballs to look and see where one of those x-intercepts is. And I saw, when I looked, an x-intercept at negative 2. So I'm going to start my synthetic division with negative 2. Okay, go away. Come back when you're done. What do you mean you didn't get a remainder of 0? But this is one of the x-intercepts. You saw it on the graph. Let me ask this question. Did you remember the 0 placeholder for x squared? Because we go from x to the third to x. So you really need to be doing negative 2 into 1, 0, 1, 10. Okay? Don't forget the 0 placeholder. That's a recipe for getting the problem wrong. You do. Bring down the 1, we get negative 2, add, we get negative 2, multiply, we get positive 4, add, we get 5, multiply, we get negative 10, and there's the 0. Okay, so finish it up. Give me the fully factored form of this, and show me a graph. Welcome back. So this is what mine looks like, and I can't factor that. So what is it I'm supposed to do? Right, that's a quadratic, and I want to know when this is equal to 0, so I'm going to have to do x equals negative b plus and minus square root of b squared minus 4ac all over 2a. There's 20. There's 4 minus 20. So that's going to be 2 plus and minus square root of negative 16 over 2. Ooh, 4i. 2 plus and minus 4i over 2. Pool noodle alert. Remember, you want to factor a 2 out of everything. 1 plus or minus 2i over 2, then we can cancel. So these are my complex roots, and now I feel like I'm ready to write the factored form of this polynomial. I have my original x plus 2, and then I have these, x minus 1 plus 2i, and x minus 1 minus 2i. Okie dokie. And the only thing I know is I've got an x-intercept at 2 and a y-intercept at 10, and I'm willing to say something like that. And you should graph it and see how close we are to it, right? Okay. I have a couple more of these if you feel like you want more practice. I think if you can do what we've done, that's plenty hard enough, and that should be good. But I do have this last problem. Find all the zeros of f of x if x minus b is a factor of y equals x to the third minus 2bx squared plus b squared x. Hot dog! What the hell, Mr. Kukla? You want me to do what now? Well, yeah, I do. I've given you one of the factors of this polynomial, and I'd like you to find the other factors. And there are a number of ways to do this. This would be a perfect problem for breakout room, because you and your partner could talk about different ways you were each thinking about doing it. Maybe we should look at some different ways. So the first thing that I think about, because I will admit to being that kind of old school person, is I see a GCF. So I can take that GCF out. And now I have this. And because I'm an old school person, my 9th grade math teacher made me learn to recognize a perfect square trinomial. I know this is going to factor as x minus b times x minus b. And don't forget the original x. Now, yeah, x minus b is one of my factors. In fact, I have a bounce at x equals b. Who knew? And an x-intercept at 0. So my zeros, because that's what we were asked about originally, are at x equals 0 and x equals b. This is not an ordered pair. These are x values, x equals 0 and x equals b. So that's one way to do it. But what about, look, they gave me a factor. I could do long division. I could turn that factor into an x-intercept and do synthetic division. Let's see how that works. b, 1 minus 2b plus b squared. Right? I'm just taking the coefficients. 1b minus b minus b squared, and I end up with 0. Fabulous. So this was, well, wait a second. This was x to the third. And we did one division. So this is x squared, and this must be bx. Oh, but look, this is factorable. I can take an x out of each of those and have x minus b. Is this my answer? No, don't forget this one. So it's this stuff times x minus b. Remember, we should always be able to FOIL our completely factored form back to our original third polynomial. Okay? This is tough. This is thinking. I will say, no, I don't think I'd do that to you on our test, but I can imagine that showing up on the SAT. Yeah, and if you're moving on to calculus, being willing to engage with some thinking like that, that's probably a good thing for you to experience. All right. Well, I hope you have a fabulous day. I hope this was a learning opportunity for you, and we covered some of the things that you're scared of and addressed them. And, well, the box problems are not going away. Okay. Take care, everyone.